with Romain VIALA, who is first year PhD student at the Femtoist Institute in the Department of Applied Mechanics. And Romain will be talking about model-based decision support for musical instrument makers.
Thank you, Melissa. So, hello everyone. So I'm going to talk to you about vibrations, as Vincent said earlier. But this time it will be about the musical instruments made of wood. So we'll talk about materials, we'll talk about wood, and we'll talk about vibrations. Little presentation plan. So first time we'll speak a little bit of about laboratory, then the context and the aim of this PhD subject. The numerical and prototyping material properties subjects give you several examples, then a conclusion, and then a Q&A session. So a little presentation of the laboratory. So the Femtoist lab. So I think that a lot of people have heard of this lab and are in this lab. So it's there is around 700 members and about 300 permanents and more than 200 PhD students. This PhD subject is made in the Department of Applied Mechanics. So this one, Mechapli. And it's made in two main themes that are about composites and durability and the robust conceptions of structure. So this one is for the material properties and this one is for the vibrations. The context of the study is that stringed instruments, they require selected woods, finely selected woods, and traditional instrument shapes. They don't change a lot within the time. And the craftsmanship that is acquired through extensive practice and through a master through apprentice. But there is no competition for instrument maker because there is the arrival of low-price instruments on the market. So nowadays they work more about repairing instruments or making preset operations, and they don't build a lot of new instruments. So we are wondering if the modeling approach and numerical optimizing can be helpful toward this industry or this craftsmanship. And it's usually used for the transport, aerospatial industry, aeronautics, and we want to switch it into the musical instrument studies. So we use the computing power of a personal computer. So almost everybody's got a personal computer. So we want to provide a tool that will be easily accessible for everyone. So the aim of the PhD subject is really to transpose numerical methods from the industry. We can see, for example, an engine of plane, and we want to switch it into a practice that goes through decades from a long time. I want to give a free decision support software. So I want to make it free because it's not an industry that's got a lot of money. And it's only a support software. We will not say it will work like that. It's only some help. So what's happening when the musicians play with the bow and strings, with an instrument, in an environment and for an audience, and the audience likes it. It's very hard to explain. It's very vast. It's very pluridisciplinary approach. For example, from acoustics through physics, through psychology, psychoacoustics, for example, material studies. Rooms, acoustic studies, a lot of different domains. So we want to focus only on the instrument, this part, but we can speak a lot of all the parts. So the numerical prototyping, which is called the FEM method, the finite element method. In fact, we have to model a structure and solve equation motions for this model, focusing on vibratory behavior. So we want to wonder how does the structure will vibrate, just like, for example, a plane can vibrate, that kind of thing. We divide the space in several elements, as we can see here, with nodes. They are linked together, and so it creates a mesh. And we implement in that material properties. Material properties are, as we use wood, they are defined here, and the wood is quite special because it doesn't have the same behavior if it's in its longitudinal way or radial or exponential. So it, all the directions means different behaviors. So we can see it. And from the trunk into the microscopic scale, it's really there is a lot of different scales in this problem. So we will only focus on not too much microscopic scale because it's not the aim of this study. There are a lot of studies about that. We're not studying the trunk because it's not like, for example, that kind of wood. We don't use it to sustain a roof or that kind of thing. We use it in order to vibrate. So it's special samples, and it's more like this one. So the components of violin, there are different types of wood. It's like spruce for the soundboard, maple for the neck, the sides and the back, ebony for the fingerboard, rosewood, ebony or rosewood, it depends on the instrument maker. And there is a bow which is made of Pernambouc. It's so those are tropical woods, and spruce and maple are woods that exist in temperate states. So it's a quite complex structure that's made of more than 30 different parts and more than 3 different woods, and they are always in different orientations in the structure. The example of a simulation is the CAD, computer-aided design of a violin, and we have made a numerical model corresponding to this one. The advantage is that it's an easy customizable CAD. So we only have to change, for example, one number, and and several pieces will be different. So we can compare them. And so here is the structure. And we can see, after that, several vibration patterns. For example, here we can see, I didn't talk to you about the bridge is where the strings are lying on, and they are, then it makes the link between the strings and the soundboard, which produces sound. So it's called the bridge. So here we can see a bridge that always vibrating. Basically, when it's red, it moves. When it's blue, it doesn't move. So it's vibrating at different frequencies. And we can see how when it's in the violin, its vibration behavior is changing. So we want to quantify that in order to give more precise presets for example, for the bridge, to make it more adapted to a certain violin. So we can make computation results and experiments, because when you have a model and you don't know if it's true, well, it's very hard to use it. So we want to make simulations and real experiments in order to compare the two behaviors. Here is the behavior of the model. So this violin doesn't exist. It only exists in 1 and 0s in the computer. This one exists, and we are making tests on this one. We are simulating the same kind of tests, and then we are comparing curves in order to know if, for example, between 2000 and 3000, if there is the same bridge than in the reality. And then with that, it's a criterion that helps us to check if the model is wrong or not. It's true or false. So several samples of results. For example, we call it the Chladni experiment. We put some sand on the structure, make this structure vibrating, and the sand goes where the structure doesn't move. That's why there is that kind of patterns here, and the black thing is the sand that doesn't move. And if we compare this with our model structure, we can see sometimes the same behavior and the same nodal lines. It's called nodal lines where it doesn't move. So it's blue and blue like that. That's several different kind of criterions that we might use. So it's the back of a violin. It's made in maple, and it's so we use several comparison criterion. And here we're comparing if it's red, it's better, because if it's red, it means that the behavior of this one is the same than this one. And if it's blue, for example here, it means that the behavior of this one is not the same than this one. So it's kind of a matrix of model autocorrelation. So the advantages of drawbacks of this method is that it's quite rapid method. It's inexpensive because everyone has a computer, and if we make it with the free software, it will help to make some free experiments and virtual experiments. It's powerful and it's sturdy. But there is several drawbacks, such as the software with unavailable license. That means that for this moment we don't use free softwares. We use software with very expensive licenses. So it's a problem right now. And we need to create interfaces in order to make it be used by the most people as possible, and not only people that know to use a script. And there are several material lockers, such as different behavior of the materials, such as viscoelasticity of the materials or damping of the materials, that kind of lockers. The conclusion we are to the perspective and the thing that we want to do with this model is to indicate what are the most important parts of string and instruments. We have to study the material to increase simulation viability, so in order to make more robust and more true models. We have to compare models and real prototypes to check the reality of the model, and we have to develop the software that will be used. So thank you for your attention, and yeah.
If you have any questions.
Do you play violin?
What?
Do you play violin?
Yeah.
Yeah. Oh, and I thought I will contact with other violin players to know about.
With violin players and instrument makers. Yeah.
I mean, the vibrations. Is it a problem when you are playing?
It's not a problem in my case. In the case of Vincent, it might be a problem, but in my case, we want vibration because we want acoustic. And we want the acoustic, the vibration create acoustics. But the problems with the vibration are really, yeah.
Just, I mean, when you are violin playing, when you and maybe the vibration with your hand. Or
Yeah. Yeah, we feel that. As for example on the guitar, you can feel the vibration.
That's important when you are playing.
For example, it's one of the criteria that is important when you build the violin, because if you can, in order to tune the vibration of the neck with the vibration of the body, the musician, by playing, will feel movements and vibration is in his head. And so we will think that it means that the violin is alive. So it will be the most preferred violin if it vibrates like that, and we want to, for example, tune the neck and the body. And you feel vibration by playing. And the vibration of the soundboard creates the sound. So have I on the floor to your question?
Yes.
With your software, we can create a new violin.
A what?
Created a new violin, new instrument.
A new form? Yeah, of course you can. Well, for example, I'm working on the existing shapes, but you can create new shapes. For example, for the guitars, you can make new designs of the bars of different stiffness in order to test if what's the impact of this change.
And for a particular musician, we can create a particular violin.
Yeah, that's the aim.
The best for him.
The best is quite subjective. That's
for a particular music, for example.
Yeah, in order to have several different sounds. Yeah.
In a room concert particularly.
Yeah, for example, in order to make it quite tuned with the room or that kind of things. Yeah. But it's a different level because we have after that we have to model the acoustic behavior between the vibratory behavior through the acoustic behavior, and after that in the room. So it makes a lot of parameters.
Thank you.
I have two questions. One of your aims, from what I understood in your conclusion, was to try to discover the most important parts of the violin. I was wondering if you had discovered that. And the second, I would like to know if your results will be applied to other stringed instruments, or if they can be applied to other stringed instruments.
So I will start with the last question. So yes, it's possible to test it with other stringed instruments, because it's not the same behavior for horns or brass. It's not the same physics. But for the violin or the guitar, the kind of string instruments, it works because there is already some guitar model, for example. Guitar models or cello or that kind of instruments. And for the first question, so the most important parts, I meant the most important part and the most important parameters of the wood in those parts. For example, we've seen that when we compare the vibratory behavior of the violin, what's the most important is the densities of the top and the back, and after that is the stiffness of the top in a radial direction. So we want to create, well, to check what's the most important and to create a ranking of the most important parts. For the moment, it's the soundboard, as its name indicates. This one, the most important part, the part that participates the most in the vibratory behavior of the violin.
May I add another question?
Yeah.
Possible? What is so special about the Stradivarius? Technically speaking.
You've won the prize for the best question. No, well, I think that we should consider it as art pieces, just for example as paintings. And I think that it's an anecdote with Gaskai Fetz, who was a violin player. And someone told him, your violin has a beautiful sound, and he took the violin, put it in his, near his ear, and he said, I'm sorry, but I hear nothing like that. So that's why the most important is the musician, and what's important about the Stradivarius, that they are well made, they are beautiful, but there is also a fashion for all the instruments. There's a fashion. There is an inflation on the price of the instruments. There is a speculation on those instruments, and they all belong to banks that want to make some kind of legend around that in order to make their price getting higher. So it's hard to compare it with other things, just like if we take 10 pictures of the Joconde and with the original in that, and we ask it to you, what's the best one? It doesn't have much sense. But for the sound, I think that it's really subjective. Because blinded tests have revealed that most musicians and public prefer recent violins. It's the works of Claudia Fritz, and it's a musician also. They prefer new violins.
I'd like to take you up on that very last comment about the preference for new violins. Does that include for ancient music and Baroque music?
Okay. The Baroque music is, I know that the tests have been made with recent compositions. Well, not recent, but not Baroque music. But there is also Baroque violins that are built in this time, recent. I don't know the difference between Baroque music or more classical music has been done. I can answer it to you. But we have one thing to know is that all the Stradivarius doesn't have the same shape that they had when they have been made, and they have been made as Baroque violins, and now they are all classical violins because they have all been rebuilt, not rebuilt, but they have had several modifications to change their properties in order to fit the new operas and the new pieces. So really all the violins and Baroque violins, I think that it's hard to find. It's not very, they are all been changed within time.
Thank you.
I have just two questions. First one, when comparing the test from measurements and the simulations, did you get the same responses?
They're the same responses. That's not the same frequencies of vibration, but they're the same responses.
Okay.
For a sample, for only one piece, not for the whole structure, because for the whole structure it's a little bit harder to find the same violin that my model.
Okay. I wonder also when you use acoustic analysis and simulations, how can you ameliorate or optimize the final sound? You are playing on which parameters exactly?
Yeah.
You reduce the damping, you are increasing the stiffness. What are you doing exactly? How can you find the best violin? Which parameters should have or must have the best violin?
It's a sum of different parameters. For example, the stiffness of the wood that's used, it's the CT, so it will work on the frequencies. The thickness of the table and of the back is very important. You have to check all the thicknesses in order to make it behave in a static way that we want. Well, what are the other parameters? The strings, the different kind of strings, the different kind of angle of the strings on the structure, the shape of the F holes at here, the reverse of the neck, different kind of reversing. A lot of parameters. Well, even if all the violins seem to be the same, they are all different because there is a lot of different parameters that you can change, as it's made by hand, not made by factory.
When you compare the model shapes, how can you know or predict if this violin is if we manufacture this violin, we will get good sound finally from just the model shapes.
So you're working with Scott Kogan, so
yeah.
you've heard about the robustness.
Yes.
And you want to make robust models, so it means that even if we got several uncertainties in our material parameters, for example, we can make something that in an area will have the behavior that we wanted, even if there is a little change in the parameters. That's called the robustness in the models.
Okay, thank you.
I want to know that it's not difficult to transform the acoustic variant to electric variant. The method to transform the acoustic variant to electric variant.
Okay. In fact, the electric violins are not the same because they don't have, for example, a body like this one. It can be only a beam, and it will be used. You have to measure the vibration of the string, and one thing, for example, that get vibration and transform it into electricity is piezoelectric, or it's piezoelectric materials, and so we put it in the bridge. So we will get the vibrations and we'll transform it into electricity, and you make it into an amp, and it will make a...
It's like a guitar?
What?
It's like a guitar?
Legator?
Yes.
Legator?
Guitar.
Like the guitar, okay. Several guitars, yeah.
Or there is a difference between the two instruments?
For the guitar, for example, there are electromagnetic mics, and so the electromagnetic mics are measuring the movement of the string, which is over this mic, and so it will transform it in electricity. And a violin, it will be a bit hard to put a big mic, for example, here, so it's more the piezoelectric method that's used.
Only big mic?
Because the mics need copper. They need copper in order to make. They need copper. They need alnico ferrules, and so it's heavy and it creates a lot of weight, and so it's not light. The weight it's not like on the violins, because for the comfort and for the vibrations. It's on the guitars. It's less impacting.
Yes, thanks.